All right, today we are working on inverse of relations and functions. So to graph an inverse of a relation, all you have to do is reflect each point across the line y equals x. That line right there is what we call our inverse line. So you just simply graph them over that point, y equals x. Remember, if we were to graph this line, this has a slope of 1, a b value of 0, because there's nothing along there with that x after it. So it goes right through the origin and just goes up 1, over 1, up 1, over 1, up 1, over 1. So that's our inverse line. So this is equivalent to switching the x and y values in each ordered pair of the relation. So that's the other way we can figure out what our inverse is you simply just take your x and y values of your points and you flip them, and that's going to end up being your inverse. So remember, any relation can be written as a set of ordered pairs. So if we look, for example, at this first graph we have here, this first point is x is 0, y is 3, because if you look at our scale going up, we're going up by 2s, 2, 4, 6, 8, 10, and it's about halfway, so I'm going to say that's 0, 3. So then this point would be the point 1, 6, because again, scale's going up by 2, so halfway would be 1. This one's going to be the point 4, 9. And then this point is 6, 10. And then our last one is 10, 11. So those are all our points there in our graph. The domain of all possible values starts at 0, goes up to 10 on our graph there, because there's no arrows, so that graph's not going to keep going, so our domain is simply from 0 to 10. Remember, the other way we could write it in interval notation would be with brackets, because those points are included, 0 to 10. All of our possible range values, well, our lowest range is a 3, highest range is 11. So again, we could be going from 3 less than or equal to y less than or equal to 11 if we did it in inequalities. Interval notation would be brackets 3 up to 11. So now we want to use our intervals or our inequalities here because we've got that line connecting those points. So it's going to be all those values in between those numbers also. It's not just simply like for our domain 0, 1, 4, 6, and 10. It's all those numbers in between also. So that's just a quick little review of what we've done. So over here, to write the inverse of the relation, you just have to simply switch the places of your x and y in each ordered pair. And then that's going to give you your inverse. So here's my original function over here. To get the inverse again, all we're going to do is switch x and y. So then my first point ends up being the point 3, 0, because it started as 0, 3, so I flipped them. And then it would be 6, 1, 9, 4, 10, 6, and 11, 10. Those are the points we'll use to help us graph our inverse of that first original function. So let's plot those points. So 0 or 3, 0 is going to be on our x-axis right there, about halfway between 2 and 4, because our scale is going up by 2. And then 6, 1 is going to be about there. And then 9, 4, about there, and 6. And then 11, 10. And then we'll connect them. There we go. There's our inverse graph. So again, easiest way, just flip your points, but as I was saying, it is also a reflection in that line y equals x. which would be this diagonal line right here, going through the two of them. So as you can see, after you have it drawn on there, if we took our papers, folded it over that line, y equals x, our two graphs would line up. Those are our inverses. So of our new graph, all possible domains would go from 3 less than or equal to x, less than or equal to 11, or 3 bracket 11. And then our ranges would go from 0 to 10. So we look at our domain and range from the original function and then its inverse. What ended up happening? They switched. So whatever your domain is of your first graph ends up becoming the range of your second graph. Since we flipped our x and y values, your domain and range is also flipped. So the domain from the first one becomes the range, and the range from the first one becomes the domain. So those just flip also. So if you can figure it out from the first one, just flip them, and that's going to be your domain and range for your inverse graph also. So those end up getting flipped. So here we got two graphs. We're going to find the inverse of each relation and state whether the inverse is a function. So looking at the first one, I got a table of values here, so I'm just going to flip-flop my x and y. So negative 1, 1, 0, 2, 1, 3, and then 1, 4. So is that inverse a relation or a function? No, because we got that repeated domain value, so not a function. So in taking a look at our second one there, we just have our mapping diagram, so I'm going to just flip my bubbles. So 285 gets written in my first one, because remember that first one always represents your domain. 731 is going to get written in the second one, and we just have to reverse our arrows. So 7 goes to 2, so 2 is going to go to 7, and then it was 3 to 8, so that will go 8 to 3, and then 5 to 1. So then is this inverse a function? It's a function. So sometimes, even though it was a function to begin with, once you take your inverse, it's not always going to be a function like in that first one. And then sometimes it still is. So follows the same rules to test if it's a function. Vertical line test if you have a graph. Looking at your domain if you don't. So here we're going to practice graph the inverse of W on the grid to the right. Is the inverse of W a function? So first thing I'm going to do, because it makes it a little easier, is I'm going to make a table of values for what they already have graphed over there, which they're calling W. So then I'm going to write down the points that I have over there. So we got 1, negative 3 is my first point. And then 2, negative 1. And then 3, 2, and 4, 2. So those were what we have. So now I'm going to invert them. Inverse. So I want negative 3, 1, negative 1, 2, 2, 3, and 2, 4. So once you have your table copied down for your new inverse, go ahead and plot your points. Negative 3, 1. Oops. I went down when I should have gone up. Negative 3, 1. There we go. Negative 2, 2. 2, 3. And then 2, 4. is that new inverse a function? No, because of right here. This would fail our vertical line test, not a function. So if you have a graph, table of values, all you got to do is switch those points x and y. Those ones are nice and easy. There's a few more steps though if you have to find the equation of an inverse. So let's say we have over here in my example, we'll start with an easier one, f of x equals x plus 4. So first thing we want to do is change f of x to y. So change f of x to be y. So I'm going to go ahead and do that over here in my example. So now I got y equals x plus 4 instead of f of x. So then second step, you're going to switch your x and your y. So I'm going to go over here, switch my x and y. So instead of y equals, it's now x equals y plus 4. So then our third step, solve for y. Like all equations, it's got to be y equals. The only time we have an x equals equation is if it's a vertical line, and it's just x equals a number. So over here, I'm going to subtract my 4. So I have x minus 4 equals y. And then our last thing is you're going to replace y with the correct notation, which is f to the negative 1 of x. That's how we write our inverses in function notation. So over here, my example, f to the negative 1 of x equals x minus 4. That's going to be my inverse for my example there. So 4 pretty easy steps. Keep practicing them. That's how you're going to commit them to memory. So for the function below, graph f and f to the negative 1, so that's the original and its inverse. Write the equation for f to the negative 1 and state the domain and range of both f and f to the negative 1. Determine whether f to the negative 1 is a function. All right. So let's first graph the original function. So f of x equals x squared plus 2. Let's start with what we have. So let's go ahead, put that into our calculator. Let's get a table of values. Get my calculator to open up there. This one's going to be a parabola because it's got that x squared term in it. I'm going to clear out what I have there. So I want x squared plus 2. I'm going to hit zoom 6. See, there's our little parabola shape. So table, we want numbers that are actually going to fit on our graph. So if I look back at my graph, looks like the highest it goes to is 6. So I'm going to want to copy for my table from -2 to +2, because those are the values that will actually fit on my graph. So -2, 6, -1, 3, 0, 2, 1, 3, 2, 6. So once you have your table copied down, go ahead, plot your point. Draw your graph. I'm going to label it simply as f of x. We don't have to write the whole equation when we've got our function notation. We can just identify which function we're talking about. That one's f of x. They also want us to state the domain and range for both of them. So I'm just going to go ahead and do my domain and range now for my first graph, my function there, f of x. So it's got arrows on both ends. So this one's domain is going to be x is an element of the reals. So x could be every single number. My range, though, we've got a minimum value here of 2. It's never going to be any lower than 2. So our range is going to be y is greater than or equal to 2, because our graph is going up, so it's greater than. And I think that's all we had to do for the f function. They want us to graph it, state domain and range. Everything else is off of our inverse. So we don't know our equation yet, but we can still graph it. Make sure you keep writing this one as f to the negative 1 because it is a different function. So all we have to do is take our first function, switch our points so we can draw our graph. So 6, negative 2, 3, negative 1, 2, 0, 3, 1, 6, 2. So once you have those, go ahead and plot your points. Because it is an inverse, it's going to end up being a sideways parabola there, which we have not seen very often yet. All right, so next part is they do want us to come up with the equation for f to the negative 1 of x. So I'm going to take my original equation over here. I'm going to first change it so that instead of f of x equals, it's going to be y equals. That was always our first step, change it to be y. Second step, flip your x and your y. So now it's x equals y squared plus 2. So now we solve for y. So I'm going to subtract 2, x minus 2 equals y squared. And then how do I go from just y squared to just y? Square root. But when we do the square root over here on the left, remember it's plus or minus the square root of x minus 2. We got to remember those plus minuses. The plus is what gives you the top half of the graph. The minus is what gives you that bottom half of that graph. So you got to make sure you have both parts to it. And then our last thing is we just have to rewrite it to be f to the negative 1 of x. So there's the equation of our inverse. Of the inverse, we still got to do domain and range. And then we got to tell whether it's a function or not. So for our domain, you can even look at your graph. What's our lowest x value there? 2. So x is greater than or equal to 2. Remember, you can just take your range from the other graph, and that is now your domain. So instead of y, though, we use x. So therefore, our range could be everything, because that was your domain from the first one. So now it's your range of your inverse. So it's just flip. So then our last part, is our inverse a function? No. It would fail the vertical line test. Like, for example, if I drew a vertical line here, it would hit twice. If you looked at it, your table, you have domain values that end up getting repeated. So not a function. So the only time that the inverse is actually going to end up being a function is if the original function was a one-to-one function. You remember one-to-one? One-to-one function. It passes both the vertical line test and the horizontal line test. That's how we know it's one-to-one. So if the original function is one-to-one, your inverse will also be a function. So for example, if we go back to the one that we just did with our parabola, it was a function because it would pass the vertical line test, but it would fail your horizontal line test. So that's our hint right there. It was not going to be a function for your inverse. But there is a way. You can restrict your domain on functions so that they end up being a one-to-one function. So if we look here, we have an absolute value graph. So we've got that V shape. It would not be one-to-one because it will fail your horizontal line test. It hits twice. So in order to make your inverse a function, what would we have to get rid of? You'd have to just get rid of one of these diagonals, right? Because if you have just one diagonal, it would be one-to-one. But the two of them together is what makes it not one-to-one. So if I were to get rid of, say, this, would I have a one-to-one function now? Yeah. So I got rid of just my negatives. So if my domain simply was x is greater than or equal to 0, getting rid of your negatives there, your inverse of that would end up being a function. So if the original is one-to-one, your inverse is a function. So if we restrict that domain to simply be greater than or equal to 0, so all the positives, the inverse will end up being a function. So how about for this one, though? I don't want to use 0. Let's see here. Where's my turning point? 1, 2, 3. So when x is a 3, that's where my turning point is. So again, if I wanted to get rid of, or if I did get rid of this half of my graph, then it would be one-to-one, and therefore my inverse will be a function. So that means we want to keep when x is greater than or equal to 3. Now, it doesn't have to be greater than or equal. Those are the ones we typically see. You could get rid of the other half of the graph. So like I could have gotten rid of the right side instead and made this less than or equal to 3. That would have also worked, but the point is you got to cut off half of it. You got to get rid of half of that graph so that it's one-to-one, and then the inverse will end up being a function.